Today, I want to start off looking at kind of our roadmap, where we are and what we have left to do in this multivariable calculus business. The big idea is that we have the pieces of calculus understanding. We've got derivatives and we've got integrals. We know how those things work for functions of one variable, and sometimes even relations between two variables that aren't functions. So the first place that we go here in Calc 3 is to upgrade our functions of one variable just to functions of two variables. That's it. We just add another variable, but we keep ourselves inside these little function box. So to that end, we describe a single variable function by saying y equals f of x is a one-dimensional curve in two-dimensional space. When we add another dimension, another input, we're still putting in two real numbers and outputting a real number, one real number. The result is going to be a two-dimensional surface in three-dimensional space. So if we consider the floor to be the xy plane, this wall is x, this wall is y, that lower corner is the origin. So the floor is where z is equal to 0. At every point above the xy plane, we'll have a height above that point. That's the same way we build the graph of a function. At every input x, we calculate the height of that point, and then we connect all the dots to make a curve. Here, we're going to take every point above the floor and raise the floor up to that height. So we're going to have this big wobbly floor that will tell us the shape of the surface. So instead of taking the x-axis and bending it up at different heights, we're taking this whole floor and bending it up at different heights. So I realize that this floor isn't flat, but the floor thinks it's flat, and that's all that really matters. The floor actually doesn't think. I have checked. I have checked for sentience of the floor, and either it's really good at hiding it or it is not sentient. So I cannot 100% rule out that the floor is not sentient. Nor can I rule out the sentience of the actual building in which you're conducting. Because there is a small possibility that it's just really good at hiding. What are we talking about? Oh, yes. So we just start there. From there, it's not covering everything. We can see up here above, what if we have more than two variables? That's not too bad. We just start throwing on more dimensions. A function of three variables will be a three-dimensional solid in four-dimensional space. That's no problem, because we'll just take three inputs and output one. So at each point in this three-dimensional space, we'll plot a height. And so we'll take the whole three-dimensional space and morph it out into whatever shape. But that's in four dimensions. It's really hard to picture. So then we start doing then what we've done is we've said, here's how to take derivatives. Here's what derivatives are for. So we've learned to take derivatives, and we know that the motivation behind derivatives is to find the slope or the equation of a line tangent to a function at a given point. What is our best linear approximation of a function at a point? That's the purpose of the tangent line. Where are things headed? What point did we go through? And where are things headed at that point? Same thing happens when we have a tangent plane to a surface. Saying, where are things, what's going on at that point? That's the point that we need. And then how is z changing in the x direction? How is z changing in the y direction? So where are things headed? If we were standing on this surface and we were very small, what would it look like? We would be standing on what we observe to be a plane, but that's only because we're looking at a very small part of it. Just like when we stand out on the surface of the earth, we look around and say, this looks flat. Welcome to Chicago. Everything is flat. The outskirts of Chicago, because everything looks like building. And go to Midwest, everything looks flat. But that's only because we're very small compared to the surface that we're standing on. If we're standing on the surface of a basketball where we are large compared to the basketball, we say the surface is curved. That's why I keep falling off it. So that's how we interpret derivatives. And then we want to talk about applications of the derivative, which we haven't done. So if you're like, oh, well, I don't remember that, that's because we haven't done it yet, beyond find the equation of the plane tangent to a function at a given point. But what were the applications of the derivative? The applications of the derivative were any, the way we interpret the derivative is any way we interpret the slope. How is y changing with respect to x? If y is distance at time x, then our slope is velocity. Well, actually, I said distance, right? Our slope will be speed. So the first derivative will be speed. If the function is a function of cost as a function of units produced, then our derivative will be cost per unit, our marginal cost, how much it costs us to make an additional unit. So all the applications of the derivative are just applications of slope. When we think, what do we use the derivative for? What do we use the slope for? It's the rate of change. If our function is velocity, then our rate of change is acceleration. Our applications of the derivative are exactly those that are the applications of the slope. Anytime you would want to do a slope calculation, that's a derivative calculation. One of the other big things that we do there is find local maximums and minimums, that is optimization. When we upgrade to functions of two variables, not a lot changes. We're going to look at rates of change, but instead of just rate of change of y with respect to x, yawn, boring. How is z changing with respect to the x variable? How is z changing with respect to the y variable? So instead of just considering, say, a function of the number of units we produce, it could be, we could be analyzing our business as a function of the number of units of labor we have and the number of units of equipment that we have. Most businesses don't consider those things very different. Labor is just more annoying equipment because you're not actually a human being from a business perspective. All right. Interesting story about that. At one point, because we like to think, like, oh, no, human beings are all valuable, immeasurable value in a human being. And from a philosophical standpoint, that's true. But at a certain point, some people had to get together and decide what was the dollar value of a human being. Because we're going to put them in planes and then send them over to drop bombs on some other people. And we need to know how many of those planes we're going to get back to decide how much money we need to put into each of those planes. You know what I mean? This is a thing that we had to do. A bunch of people in a room sat down, well, how much is a human being worth? And all the philosophers had to leave, and we just had to be economists. Well, let's make a calculation. Anyway, the nice thing is this happens a lot. We look at functions of two variables, the thinking is going to be the same. Mechanically, we're going to have to do some weirder stuff like we saw on Friday and Monday when we were taking derivatives. We had to do a little bit different stuff to find those derivatives. But what we'll use them for, pretty much the same. The other direction that we want to go is the integrals direction. That's the other big thing that we do in calculus. We do these integrals. And so we want to think about what is our core question when it comes to integrals. Most of the time, we just lead with the definite integral and say, this is going to give us the area under the curve. And the part that I like to include, and above an interval on the x-axis. So under the curve and above the interval, sandwiched between those two things. Top boundary is the curve, bottom boundary is the interval from A to B. So your definite integral from a to b of f of x to x, the a to b is your floor, and the f to x is your ceiling. So a single variable function is a one-dimensional curve in two-dimensional space. That means we're going to be grabbing an area. We say under a curve and above an interval because we're dealing with a one-dimensional thing, y equals f of x. When we talk about y equals f of x, y, we're no longer dealing with a one-dimensional curve, we're dealing with a two-dimensional surface. Underneath a surface is not going to be an area. What's going to be underneath a surface? A volume. The dimension went up by 1 all around. One-dimensional curve, boundary of a two-dimensional area. So a two-dimensional surface will be one of the boundaries of a three-dimensional volume. So for two variables, a two-variable function, our integral is going to think about, I shouldn't have written below it because I knew I was going to write above. Now I'm going to smear all this. Hopefully I've been talking enough that it's dry. Let's find out. Our two-variable function, instead of an area, we're going to go up by one dimension and we'll have the volume. You know, these are all almost capitals. There's just smaller cap. That works. Volume under a surface and above. Well, it's not going to be a region. I can't just say from A to B. That's why integration was so simple when we had a function of one variable, because we're just plugging in all the things from an interval. The definite integral from A to B of f of x dx says, take this f of x dx and plug in every single real number between A and B. That's the hard part, right? Because that's every real number. That's a continuum. We can't just pick individual ones, because as soon as we just start picking them, no matter how many times we pick, that's going to be a discrete set. So that's one of the weird things that goes on in calculus. We have to figure like I was there. We had to figure out a way to take our discrete approximation and see how that moves into a continuum. But that's beside the point. The important thing here is that one-dimensional curve, one-dimensional interval. Now I've got a two-dimensional surface, and it's not going to fit above an interval. I'm going to have not just an interval, I'm going to have some set from the floor. So the word we're going to use is a region. It's going to be under a surface, and the stuff that we plug in will come from some region in the XY plane. The region is two-dimensional. Our interval is one-dimensional. The function of the region will be the same as that of the interval. Here are all the things that you plug in to the function. The interval is just saying, plug all these things in, plug everything between A and B into the expression f of x dx. Whatever expression we come up with for our surface, we're going to take all the values from the region and just plug them into that expression. It's going to be f of xy dA, dA for area. We're just going to have to figure out a way to tell the integral, plug these values in, plug all these ordered pairs in. Once we get the hang of describing these integrals, we're going to want to think about applications of integrals. And we're going to remember that applications of integration are the same as applications of multiplication. The big twist here is that one of our factors is continuously variable. So our applications of functions of two variables are going to be the same as applications of multiplication. The difference now, when we have a function of two variables, I can say one of the factors is continuously variable in that direction, the x direction, and the other variable is continuously variable in the y direction. I get to use two different directions for my continuously variable function. Before, when we had single variable, everything had to vary in the same direction. If you recall, some of the problems were find the volume by taking the cross-sectional area multiplied by the height. And we just made the cross-sectional area variable. That cross-sectional area could be variable, but it always had to have the same shape because we had to be able to write a function. I had to say the cross-sectional area is always a circle because I only got to vary it up and down. So I could have a different circle at different heights, but it always had to be a circle. I couldn't vary how x and y were related to each other. That makes sense? Incorrect. It doesn't make sense right now because we haven't done any integrals of functions of two variables. That was a trap question. That's a tough one because I'm a figure of authority. You're supposed to believe what I say. And so the DC on that one was a 20, but that's okay. It's not lethal. It's one of my favorite traps in Dungeons and Dragons. It's the 5-foot pit. It's like you fall into a 5-foot pit. You take no damage, but it's kind of embarrassing because you're the rogue and you were supposed to be looking for traps. No hit point damage, just embarrassment. If the player describes exactly how embarrassing it is, I might use psychic damage as they're embarrassed, but only at a very high level. I wouldn't want a low-level rogue to fall into a pit, not take any physical damage, and then like die of embarrassment. Actually, now I kind of want to. The D&D club meets today at 2 o'clock up in 7322. So don't play a rogue. So all the applications of multiplication are going to be applications of integration, because integration is just trying to model multiplication. It's multiplication, but one of the factors is continuously variable. Now, the continuously variable stuff can happen in more than one direction. Any questions? It all fits together. The more I think about this, the more I think about Charlie from standing in front of his board with all the lines all connected and everything. The same thing happens when I talk about algebra, because algebra is just arithmetic. You'd be like, look, it's all connected. And I'm like, that could totally be a meme. I wonder if that would be a more effective way of teaching math, just through memes. Instead of having these like long ass 50-minute lectures, well, all right, 40 minutes because I start 10 minutes late, but instead of these enormous 40-minute lectures, just break it down into a bunch of like less than 3-minute TikTok. It's like TikTok, all of Calc 3. Someone asked me like, well, TikToks, even when they're really short, like a minute-long TikTok, it's like, oh, sure, you get it right then, but then you don't remember it later. I'm like, oh, so you're implying that if I take 40 minutes to do like 15 TikToks, everybody will remember all of them? If I just like, because everybody remembers all the stuff from my 40-minute lecture? Hell no. I can be like, tomorrow I can be like, I'll close your notebooks and draw the roadmap of Calc 3. And people will be like, oh, no. I'll be like, oh, it's worth 1,000 points. And then students be like, oh, I'll just drop this class. And then it's a big game of chicken. Do you know what I mean? It's not like you're going to remember everything I say all the time. So in those 3-minute TikToks, I would have to make sure that I pretty much say one thing like 40 times in a row. Each one can be like a minute and a half long, but I have to say the one thing over and over again. Some of you, if you were in my class for Calc 2, might have seen this coming. Integration is multiplication, but one of the factors is variable, continuously variable. If you don't remember that sentence, integration is multiplication, but one of the factors is continuously variable, it's pretty much because I didn't always say continuously. I didn't sing the lyrics the same every single time. But search your memory banks. Think back to when I first started talking about integration in this class. And when I said integration is multiplication, you knew where it was headed. You were thinking, but one of the factors is continuously variable. It might be the case. You're like, oh, I'm not really sure what that means, but that is stuck in my head. That is the song stuck in my head. Maybe I should set it to music. Now I'm trying to come up with a melody. So integration is multiplication, but one of the factors is continuously variable. Okay, I really have to put this away. I got to stop trying to come up with a melody. For integration is multiplication, but one of the factors is continuously variable. I should also try to put some rhythm to it that would go along with the melody. I am definitely not going to do, so the suggestion in the chat is a rap. I am definitely not going to do that because whenever math professors start rapping, it is so super cringy. Now, I'm not saying it's not going to be effective because the cringier it is, probably the more effective it would be, but I don't think I have enough ego to withstand doing something so cringy. So yes, but no. I mean, even my ego could not withstand that, is the thing. That's the thing. But yes. Does everybody remember the quadratic formula? X equals the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. It's not how you would say that. That could be misinterpreted, but you're only using it as a mnemonic device to help remember it. And if you can't have trouble remembering it, the first thing you add is rhythm. X equals the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. Rhythm will help. Put it to a rhythm and it'll help. It doesn't have to be an interesting rhythm. It just has to be a rhythm. And if you really want to remember it, you need a melody to go along with it. X equals the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. Then you will remember it forever. And now my great hope is that you all will be singing the quadratic formula for the rest of the day, or until you can get yourself to a playlist with song other than that, which is why I've shut down Spotify today. No! Oh, X equals the opposite of b. Stop it, stop it. Plus or minus the square root. No! What's even worse is that the quadratic formula is trash and you shouldn't use that to solve quadratic equations, but now it's going to be stuck in your head all day. So now, not only do you have this stupid song stuck in your head, you also know that the knowledge is trash that you're remembering. Anybody who says that I am not the villain of the campaign is clearly deluding themselves. Any questions? This is just kind of a roadmap. We've done this derivative stuff. We could think about where things are headed, but we want to think today about where things are headed and how they are still similar to stuff that we've already done. Now, keep in mind, this particular roadmap is comparing the single variable version of things with just functions of two variables. There's a lot more ways to describe relations than with just functions. Relations, there are relations that are not functions. like circles, x squared plus y squared equals r squared. Y is not a function of x is not a function of y. So we're going to have to figure out a way to deal with that. In that case, there's a couple of things we could do. We could make y a just two functions of x, the plus or minus square root of b squared minus 4ac. Oh, okay. Or we could be fancy and parameterize the curve. That's an important skill to have. We didn't set you up very well in the past for parameterizing curves because there were a lot of ways around it when we were just working with curves in R2. But a function of two variables is a surface in R3. That means if I want to describe a curve in R3, I can't use a function to do it. So if I imagine, we can imagine a sheet of paper just kind of like all over this room, covering the whole floor and then just raising up all the different points. That we could describe with a function. But what if instead of that, we had the path of some fly flying through the room? The fly flying through the room is just describing a one-dimensional curve in R3. We're going to need a different machine to deal with that. So there are a lot of things other than that, but we get a lot of mileage out of just going from functions of one variable to functions of two variables. Any questions? Some of you finally have answers to the graded discussion. How's everybody, okay? Are you sure? It looks very sad. I kind of know why you're sad. It's not because you're viewing the scope of all this math. It's because you're thinking x equals the opposite of b, plus or minus the square root of b squared minus 4ac. All over 2n. I wasn't going to finish that one, but I couldn't stand not to. Any questions? Comment? We just have to decide where we're going to go next. Probably applications of the derivative because I'm boring and basic. More interesting route would be to talk about integrals. All right, that's going to do it for today. This is our roadmap. We needed to stop. We did equations of tangent planes. We needed to stop, back out, take a view of where we are. Say, well, what's going on in this game? Stop focusing on the mini map, bring up the entire map. All right, that's it for today. I will see you all on tomorrow. Everybody have a good day, and thanks for playing.